I'm so old that it's harder to divide, maybe.
Yeah, that could definitely be part of it. And Elizabeth said here too, unless you're growing, there shouldn't be too much cell division happening, right? So think about it. When you're a baby, everything's growing like crazy. You're making tons of cells all the time. You guys are still making quite a bit of cells, right, compared to me, because I'm a lot older than you, right? And you're right, someone who's way older, they're going to have even less mitosis going on, especially in certain parts of the body, right? Some things probably stay pretty consistent, like skin and the intestines. They have a high rate pretty much your entire life. But other things, like if you're a baby, your stomach is going to be dividing like crazy, growing. Is it true that the older age increases your risk of cancer? Yes, right? Because as you get older, you are actually going to have repaired your DNA millions and millions and millions of times. And think about it, the more you have to repair something, the more likely it is to go wrong, right? So if you think about even your phone, right? If you drop it once and it gets a crack, you could probably repair it. If you drop it 20 more times, right, it's going to get harder and harder to repair. And that's kind of how cells work as well, right? They're constantly repairing this DNA, and the more times they have to do it, the more chances that they're going to make a mistake. So age will increase your risk of cancer, yes. And I just realized I wasn't recording this. I'm so sad. I just started recording it now. So I'm going to briefly summarize what we've done so far for people who are missing this live lesson. We just discussed cancer, what it is, right, causes of it. We went through what the mitotic index is, and we started talking about statistics and a chi-squared test, right? And now we're actually moving on to doing an example. Okay, so we have our patient and we have our expected values. Right now, these are not real. I made these up because I don't know what the expected values are specifically for this exact situation, but that is fine, right? So I did percentages here, which is something that you could easily find if you knew, 20 cells out of 100 were in interphase, you can calculate the percent. So I did that part already for you guys. So our percentages should add up to what? 100, right? Because we want to account for every single cell, which I hope mine add up to 100. If they don't, you guys can point it out to me. Right, they should add up to 100 because, like I said, there's 5 categories. Every single cell has to go into one of those categories, right? There's no cell that you're like, well, I don't know what it's in, I'm just going to ignore it. No, it's got to be counted. The top row is not 60, 70, 80, 90, 90. Are you sure? Okay. I was like, whew. Okay. Okay, yeah. Well, that was me yesterday when I was trying to make up these numbers. I was like, does this add up to 100? Okay. So just looking at this, right, our first impressions maybe it doesn't look that different, right? Maybe metaphase looks significantly different, possibly, I don't know. So now we want to do the math, right? Because you know what's 1,000 times more powerful than your opinion? Math, right? Where you can prove exactly what you're trying to say. So our first step is going to be actually to fill in our observed values. I'm going to try to split my screen so that we can see both of these things at the same time. Okay, so in your chart, we're going to start off by filling in I have too many things open, our observed values. So that should be pretty easy for us all to do. So looking at the chart, finding those observed values, oops. And filling those into our observed boxes. You don't have to write the percentage if you don't want to. And you can also fill in the expected. Oops. Okay. Okay. So first two rows pretty easy, right? All we did was basically look at the data and copy it over into our chart. Now, this is the fun part where we're going to do some calculations. So I'm going to stop sharing my screen because I want us all to practice doing this calculation. We're going to do the first one together, right? And then I want you guys to do the other ones, and we're going to see if we get the same answers. So in order to do this second box, I'm actually going to write the steps in the box so that it's a little bit easier to see. We're going to take our observed value, which is 60. We're going to subtract our expected value, which is 77.5. And then we're going to square that value. So in a calculator, we would do 60 minus 77.5. It's a negative number, right? But we're going to square it, so it doesn't matter. And I don't know how to easily square on this calculator, so we'll do it the old school way, times negative 17.5. And we get 306.25. Okay, so 306.25 is our difference squared. Okay, you don't have to write out the numbers like I did in this first part here, but you can, right? If you do, you might want to delete them just so it's not confusing to you because you want just the difference squared value there. Okay, so I'm going to stop sharing my screen. We're all going to spend a few minutes filling in the boxes for the other phases, doing the same process, taking our observed, subtracting our expected, and squaring it. And you can feel free to use a phone calculator, right? Or if you have your own physical calculator, that might be easier than doing the computer one, but that's up to you. Okay, and when you guys, so are the negatives allowed in the equation? Yes, because if you get a negative number, you're going to square it and it's going to become positive, right? So in fact, you can kind of ignore the signs in this case, right? Because if you get something negative, you're going to square it and it's going to become positive. Just make sure you're doing observed minus expected. And when you guys are done filling in that row, if you could just pop a 1 into the chat. The 1 is for you're done filling in that first row of observed minus expected squared. Okay, Ariel. We'll wait about 1 more minute here. You can move on to the next row if you feel like you know how to do it. Otherwise, we'll wait just a couple seconds and we're going to do one together. Okay. So even if you're not quite done, that's okay. Hopefully you were able to do 1 or 2 so that you got the idea, right? But these are the values I got. And now we can argue if you guys got different values than me. So check what you got. If you got something different than me, let me know and we can check it. Okay, so that was the first step, the difference squared. Our second step now is that we're going to take this number and we're going to divide it by our expected value, right? Because if we look at this box, we already have O minus E squared. That's what we did right here. Now we just have to divide it by E. So for this first one, we would take 306.25 and we're going to divide it by our expected value of 77.5. Which if we do that, we get we get 3.95161. We'll just round to the hundredth place here for now. Okay, so this second row, all you're going to do is take the value you already got and divide it by your expected value. So again, I'm going to unshare my screen, and I'm going to give you guys a few seconds. Same thing, when you finish, pop a 1 in the chat. Also, pop questions in the chat if you get stuck. Ariella says already stuck. Okay. So Ariella, I want you to take, well, I'll explain it again when we go back. I don't want to show the answers yet. But you're taking the value that you just got and dividing it by the expected. Okay, we're about halfway with people saying they're done, so we'll give some more time. And if you are stuck, don't worry. This is a interesting process to do for biology. I know you're like, why are we doing math? But I like to make connections here where this is the kind of math that you do in science, right? It actually matters for people's lives. Okay, I'm going to share my screen. If you're still working, we're going to go through the process a couple more times just to make sure everybody is on board. Otherwise, you could check your answers here. So basically what we're doing is we're taking our difference squared value and we're dividing it by our expected value. So for our second box, you should have done, oops, I don't want to write it in that box. You should have done 4 divided by 17, right? Our difference squared divided by our expected. For your third box, you should have done 144 divided by 3. What should we have divided for anaphase? $20.25 divided by 0.5. Good. And then the last one, we should have done 9 divided by 2. Okay, so you're just taking, literally you're doing this box divided by the one right above it is the pattern, right? But you could also think of it as the difference squared divided by E, or the expected. Okay, so now comes the easiest part. We add all of these values up and pop them in this last box here because we want the sum of all of these differences squared divided by E. So we're just going to add them up to get our chi-squared value. 3.95 plus 0.24 plus 48 plus 40.5 plus 4.5 equals 97.19. Oops, I don't want it to be that gray. So this value right here, that is our most important, our most important value that we're getting here because that is our chi-squared value. So again, you can use the chart if you felt like that was easy and quick, or you could straight up just do the equation step by step in the equation as well. Some of you might feel more comfortable doing that. But this is our chi-squared value, or our x-squared value here. So now the next step is to look at our critical value of chi-squared. Right, here's our table. I know it's kind of weird font, but it was actually the best one I could find, disturbingly. So I already told you guys before that our degrees of freedom is 4 because we have 5 categories and we subtract 1. And remember, we're adding up each category, so it's going to matter the degrees of freedom. We are going to be looking at 0.05. So we see here that our critical value of x squared, or chi-squared, is equal to 9 point, where did it go? 488. Okay, that's the value that we're going to compare to. We got 97 point, what was it? Scroll up thing. We got 97.19. Okay, we got 97.19. Is that higher or lower than our critical value? Oops. I'm just going to say it's 97. So it's so much higher. So what does that mean? That means that our value of x squared is greater than our critical value, which means this is statistically significant. So basically what you look at to determine statistical significance is your, what is going on? Is your value higher or lower than the expected or critical value, right? It's much, much higher. This would really tell us, like, ooh, this is a problem. This person's cells are doing some weird stuff that they shouldn't be doing, right? If we ended up getting a value, let's say that when we did our table, let's say that we got 4.2, then our value would be less than the critical value. So we would say it's not statistically significant, right? It's not different enough. Essentially, we want to be thinking about if it's less than the value we say is our critical value, then we're good to go. If it's greater, that's not good. Okay, so let me try to figure out how to get rid of some of this stuff without making it all disappear. All right. So in Oh yeah, I have the PowerPoint over here. I was like, where'd the PowerPoint go? So what that means, right, is what is our chi-squared value? Well, we got 97, we say, and our critical value was 9.48, right? So if x squared, what we got, is less than the critical value, it's not cancer. Well, we had the opposite. We had that our x squared was greater than the critical value, which means that person most likely has cancer. Okay. So what I want you guys to do now is, for an exit ticket, I want you to do the same thing for a different patient. Okay, so I have the observed and expected values here. You can do the same exact process. You can use the chart. You could use the equation, right? Whichever one makes sense to you. I know we only did one example because this takes a while to do, right? So now I'm going to take questions about any of the steps. If you want me to repeat something, or you're like, wait, what did we do there, right? I'm not sure how we got this number. Let me know, because then what you're going to be doing is you're going to show your work for your chi-squared value. You're going to explain what it means. Is it statistically significant? And then you're going to summarize what cancer is in your own words. So the first two are complete math, and the last one is summarizing cancer. So looking at the data for patient 2, right, looking at the chart, I want you guys to let me know if you have any questions, if there's any parts. The final step using the chart confused me. Okay, good. So we'll go over that first. Okay, so using the chart, since we're doing the same mitosis problem, right, that actually is convenient because we're going to look at the same critical value. We are always going to be in this column for this class because I'm telling you that, right? We could use other columns if we wanted. And because we're always going to use mitosis, at least in this example, we're always going to be looking at our critical value of 9.488. So basically what you want to do is whatever value you get, you're going to compare to this value. If your value is less than 9.488, then it's not cancer, right? It means it's not statistically significant. If the opposite is true and your value is greater than 9.488, then it is cancer, right? And it is statistically significant. How do we get the 97 for the table? That's the value that we calculated using the chart. So 97, I just rounded, was our value that we got from up here. That is our calculated value of chi-squared. That's going to be different for this next example that you guys do, right? You're going to get a different number there. But no matter what number you get there, you're still going to be looking at the same place on this critical value chart, right? Because we are still looking at mitosis and we're still looking at the same level of error, we'll say. What do we calculate? Which variables? You're not calculating variables. You're going to do the same thing with this chart. So using the numbers that I give you for patient 2, you're going to go through the chart and do the same thing. You're going to write in your observed values, your expected values, do your subtraction and squaring, divide by E, and then add them all together. Add all of the final boxes together to get your chi-squared value. So that's why we did the chart the first time, right? Because now you're going to do the chart again with different numbers, but it should be the same process. Does that answer your question, Jordan? we're going to be using these values for our observed and our expected. We always compare with the fourth row, yes. So in this case, we're always going to compare with 9.488. If we had a different situation, like I know a lot of times when people learn about chi-squared, the experiment that you do or the work that you do in class is with M&Ms, trying to determine if the bag of M&Ms you have is statistically significantly different than a regular bag of M&Ms, right? So because you guys know sometimes you get M&Ms and there's like 20 reds and no other ones, right? So it's kind of using the same concept. Well, they would probably use a different value because there are more maybe than 5 colors of M&Ms. How many colors are there? Brown, yellow, red, blue, green, purple. There's 6 maybe? Orange, 7. So they would have a degrees of freedom of 6 if you were doing M&Ms, right? So for mitosis, we will always use the row 4 on the chart and under 0.05. But that's not what you would use every time you did this. Oh, there is no purple? Okay, so maybe there's 6. So if the number is bigger than 9.488, then it's Cancer. Yes. Total would be the percentages added together. Yes. So they should add up to 100. If I messed up and they don't, adjust them so that they add up to 100. Otherwise, it's not going to work. Yeah, so this total here is just the percentages added together. If you were using decimals, the total would be 1. It's just to make sure that all of your cells or all of your items went into a category, right? Because you don't want to leave some of them out. They all have to be in a category. Okay, other questions? And you might come up with questions as you're doing it, right? That's fine. You can turn it in and put questions on it, and I will answer them, right? So you could say, oh, I got stuck on this step, but here's what I did so far, and I will give you feedback, and then you can keep working on it, right? So it's not like you have to get this the first time immediately, right? It's going to take time to practice it. We're going to try to do another chi-squared test in the future so that we can practice using this again, but with a different concept. Can you do everything on the chart and turn in the chart? Yes, totally fine. Okay. Any other questions? Can I show the math again? I can't, Alina, because I only have 9 minutes, and it took about 15 minutes to go through that. Right, the slides are in Canvas. Yep, it should be visible to you now so you can see it. I'm going to upload this recording probably in the afternoon. I didn't record the very beginning, but I did record all the math, right? So you can actually, that chart, Victoria? So you can actually go back and watch this again and watch the math again. Okay, so if you're feeling like you need to see it one more time, I'm going to upload this. The math is recorded. You could watch the math as many times as you need to. And you could even follow along using different numbers. Okay? Okay, otherwise I would do it again, but I have to go to a chemistry virtual session in about 5 minutes. So they do not want to know how to do this. They already do enough math in that class. All right, so again, do the best you can. At the very least, turn it in with what you have done and say, hey, I need help on this part, or did I do this part right? Right, I'm happy to give you feedback. Okay, the last thing is going to be the code word, which today is that. I just typed it in the chat. Make sure you look at it. Okay, so thank you guys for sitting through some math. I know for some of you that was probably painful. Hopefully, though, you're seeing the connection here, right, between using math to help us identify things in science, right? This is going to give, if you were a doctor, this would give you a really good idea about whether that person has cancer or not. Okay, I'm going to stop sharing my screen, and I will see you guys next week. The exit ticket slide is on Canvas. The assignment just went live at 9 a.m. So you can actually go on there and you can see the whole slideshow. And I copied and pasted just the exit slide. Okay, so check your calendar. It should show up on there. Or it'll be in modules in the very last module. All right, bye everyone.